Yes. So good afternoon everyone. Yeah, hope all of you are doing good and hope all of you have done your KCT exam very well. Yeah. So today, dear students, we will be discussing the another important high weightage chapter, that is in the organic chapter, that is coordination compound, that we will be discussing each and every point that we will be discussing in this chapter. Points of this chapter we will be discussing in this today's section. And this is one of the high weightage chapter in the organic, so all of you pay attention to this class, and if you have any doubt, do ask in the chat box. Yeah, we'll be clearing everything and we'll be moving on. Yes. So hope all of you are ready. We'll be starting the coordination compound chapter. First we can go and check what are the important topics. What are the important topics covering the coordination compound chapter. The first one is about the classification of ligand. We know that ligands has been classified based on their charge as well as based on their density. So based on that we will be classifying the ligand. Then we will be going into the Vernier theory. Then the important point is valence bond theory, crystal field theory, metal carbonyls. All these are the important points that we will be discussing today. And then finally the isomerism part. Isomerism is an important one and it's a high weightage part. Yes, and along with this we will be also discussing about the nomenclature part also. Okay, first of all we can go into the classification of ligand. First we will be going into the classification of ligand based on the density. What is meant by density? What is meant by density? What is meant by density? Density is the number of donor atom present in a ligand, present in a single ligand, that is attaching to a central metal atom. That is what density means. Okay, if only single donor atom is present in a ligand, then we will be calling it as unidentate. If two or more than two donor atom is there or multiple donor atom is there, example EDTA, then we can call those ligands as polydentate ligand. Okay, example of EDT. Okay, example is EDTA. EDT, if you observe, like you can see there are nitrogen donor atom and oxygen donor atom is there. They will be binding to the metal atom. Next one is chelating ligand. What is chelating ligand? Chelating ligands are polydentate ligand. They are polydentate ligand in which they will be attaching or they will be binding to the central metal atom and will be forming a 5-membered or 6-membered ring. And remember that chelating ligands will be makes the compound stable, makes the compound exceptionally stable. I can just take an example. I am taking a oxalate. I am taking oxalate ligand. Oxalate. Yeah, oxalate is having two donor oxygen atom, O minus. Yeah, and they will be binding to the metal atom. See here you can see after when it binds to the metal atom, you can see then it forms a cyclic 5-membered structure, right? 1 2 3 4 5-membered structure. This makes the compound stable. So remember that chelating ligands will be makes the compound very stable. Next one is ambidentate ligand. What is ambidentate ligand? These are the ligand that can coordinate through two different atoms at a time, only at a time. Example, I am taking nitrito, NO2. NO2 have two donor atom. Nitrogen also can be a donor atom. Oxygen also can be a donor atom. At a time only nitrogen will be a donor atom. And in some cases oxygen will be donor atom. This type of ligand in which a single ligand can have two different donor site in which one will be binding at a time. That is what called as ambidentate ligand. The examples: cyanide, Cn minus, Nc minus, and also thiocyanate, SCN, and isothiocyanate, NCS. All these are the another examples of ambidentate ligands. Yes, these are some of the classification and some of the basic thing about ligand. Is it clear? Is it clear, students? Monodentate, bidentate, polydentate, ambidentate, all these are the basic things in coordination compound. Hope all of you know all these things already. This is just a brushing up things, just look on to that. And also I will be just giving a idea about what is coordination sphere, what is ligand, what is counter ion. Just look an example of CO NH3 6. Okay, just look an example CO NH3 6 Cl2. Okay, here we know that this bracket, what is this bracket? This bracket we will be calling it as coordination sphere. And what about this metal? This metal is called as central metal atom. And what is NH3? This NH3 is our ligand. This NH3 is our ligand. What about the Cl2? This Cl2 is our counter ion. This Cl2 is our counter ion. What is actually happening is ligand, which will be having a lone pair or negative charge, they will be donating electron to the vacant d orbital of CO. As it is donating electron to the vacant d orbital of CO, you can see this metal central metal will be generally Lewis acid, and ligand will be Lewis base. In the ionic equilibrium chapter, we already discussed what is Lewis acid, what is Lewis base. As the central metal atom is receiving electron, they are Lewis acid. As the ligand is donating electron, they are acting as Lewis base. Okay, this is just a summary of introduction of this chapter. Yeah, hope it is clear to everyone. We can move into the next part, that is a nomenclature. Shall we move, students? Any doubt anybody is having? Yes, thank you. Yes, first one is nomenclature. Nomenclature, yeah, there are set of rules are there for naming a coordination compound. The rules that we will be discussing first is cation. There will be cation and there will be anion in a coordination compound. In that, cation will be named first, then anion will be named. Okay, just like NaCl. NaCl, we are naming, the name is starting from sodium because sodium is a cation there, and the positive part of the complex is named before the negative part. Okay, then within the coordination sphere, in the coordination sphere you can see there will be ligand and there will be central metal atom. In that, ligands are named according to the alphabetical order. That is how we will be naming. And after this one, after naming the positive part, then the ligand, or then the negative part, then we will be adding oxidation state. We will be adding oxidation state, and finally what we will be doing, naming the counter ion. This is how we will be naming a coordination compound. First, what we will be doing, we will be naming cation, and cation will be there always in the left side. If I have a coordination complex, just a minute. Okay, if I have a coordination complex CO NH3 6 Cl2, okay, this here you can see the coordination sphere is coming in the left side and Cl2 is coming in the right side, which means this coordination sphere is a cation and Cl2 is the anion here. So we will be naming the coordination sphere first. In that, we will be naming the ligand first, and then we will be naming the central metal atom. Then we will be adding the oxidation state of it. Finally, we will be naming the counter ion. We can go through some examples. And thereby we can have an understanding of nomenclature. Have you understood the rules? We'll be discussing it with some examples. Yeah, all of you try it. I will be giving some examples. CO NH3 5 SO4 Cl. Yeah, CO NH3 5 SO4 Cl. What is the name of this one? Yeah, first of all, I will be giving an example for you. First of all, we know that this is a positive part and this is the negative part. In positive part, you can see there are ligand and there are central metal atom, and now we have to name the central metal atom next, and first we have to name the ligand. In ligand, you can see there are two ligands are there. In this, which ligand we will be naming first? One is amine, then sulfate. In this, which one we will be naming first, amine or sulfate? Which one we will be naming? Amine we will be naming. After that only we will be naming sulfate. Okay, because alphabetically we have to go through it. So how many amines are there? 5 amines are there. So the name is pentamine, then sulfato. Here it is sulfate, and when it's coming into the coordination sphere, the ATE will be replaced by ATO. Anionic ligand, the nomenclature when it's coming into the ligand, ATE will be replaced by ATO, sulfato. Okay, if it is anionic ligand. Okay, then what about the coordination number? How to find out coordination number? X plus coordination of X plus oxide state of NH3. NH3 is a neutral ligand, right? So X plus 0, then sulfate minus 2 is equal to 0. So X is equal to X is equal to plus 2 is the oxidation state. So we have to mark the oxidation state in Roman number. Then our ligand, that is chloride. Sorry, not ligand, our counter ion, that is chloride. This is how you have to name the coordination compound. Yeah, have you got it? First cation, in the cation, ligand first. Ligand should be in alphabetical order. Then penta means sulfato. Okay, then we have to go to the central metal atom. We have to name the central metal atom. What is the central metal atom? Cobalt. Then oxide state, cobalt to chloride. This is how we will be naming the coordination compound. I will be giving one more example. Just note it down. CrEn thrice Br3. What is the name of this one? Here one more additional rule that we will be discussing in this one. Anybody got the answer? First of all, this is the positive part, this is the negative part, and here there is a ligand. And here what is the name of this ligand? It is ethane 1312 diamine, that is ethylene diamine. It is ethylene diamine, right? But if you observe the ethylene diamine, there are 3 ethylene diamines are there. Can I use triethylene diamine? Can I use triethylene diamine? Here you can't use triethylene diamine because in the name itself there is a bi-tri. Yeah, in the name, in the ethylene diamine, the name you can see a bi term, right? Sorry, there is a di term is there, right? So we can't use di term to represent that. We can't use a di prefix to represent the number of ethylene diamine here. So instead of that numbering, we will be using bis, tris, tetrakis, like that to represent the number of ligand present in the coordination compound. So how many ethylene diamines are there? Ethylene diamine is there. 3 ethylene diamine is there. So I will be using tris to represent the number of ethylene diamine. Then tris ethane 1,2 diamine, tris ethane 1,2 diamine, then chromium. What is the oxide state? What is the oxide state? What is the oxide state of this compound? What is the oxide state of this compound? Ethylene diamine. What is the charge of this ligand? Is it charged one? Is it or neutral one? X plus 0. Ethylene diamine is a neutral ligand. X plus 0. Then bromine is there. 3 bromine is there. Minus 3 is equal to 0. So X is equal to plus 3. So ethylene, tris ethane 1,2 diamine, chromium 3, then bromide. That is our counter ion. Is it clear? Shall I give you a few more examples? This is nomenclature is clear. Any doubt anybody is having? Ethylene diamine or ethylene 1,2 diamine? Can I move, students? Any doubt anybody having? Okay. Now the next one. I am giving one more example. K2NiCN4. Name this coordination complex. K2NiCN4. Here you can see there is a cation which is outside the coordination sphere, and then anion is coming as a coordination sphere. So here you can see the left part is potassium, which is a positive part, and the right part is coordination sphere, which is the negative one. Screen is not visible properly. Is it for others also, or only for Sakshi? Okay. What's the problem? Let me check the. Okay. Yeah. Thanks for the update. Let me check the network connection. What about now, guys? Is it working well? Students? Okay, yes, thank you. So try this compound K2NiCN4. Try this compound. How we can name this one? First of all, we will be naming the left part, which is the cation, and here the cation is potassium. So potassium. Then we will be going into the negative part, which is the coordination sphere. In the coordination sphere, we will be naming the ligand first. So potassium. How many ligands are there? 4 ligands are there. So potassium tetra cyano or cyanido. You can write tetra cyanido. Then nickel. Here you can see the name of the central metal atom will be changing slightly. How it will be changing? Here you can see nickel is coming in the negative part. In remaining all the cases, the metal is coming in the positive part. So normally metal will be ultra positive, right? And when the metal is coming into the negative part, the name will be changing slightly, and the name will be potassium tetracyanide nickelate. Nickel. That is, we will be adding the suffix ate to the metal. Whenever the central metal atom is coming, or the coordination sphere is coming in the negative part, at that time you have to add ate to the metal. Then our coordination oxidation state. What is the oxidation state of this one? What is the oxidation state? It is 2. Then 2 iron. So this is the complete naming for this coordination compound. Okay, here you can see nickel, which is a metal which is coming in the negative part. So whenever nickel is or metal is coming into the negative part, you will be adding the term Ate to it. Okay. So there are some metal which comes in the negative part. They will be having some different name. I will be writing that over here. If it is iron which is coming into the negative part, the name is ferrite. It's not iron 8, it is ferrite. Then Ag, silver, it is argentate. If it is copper, it is cuprate. And if it is gold, orate. So these are the different names you can expect in the case of metal which comes in the negative coordination sphere. Okay, is it clear? I'll give one more example. Yeah, after that we can move into the next part. CO NH3 4 H2O Cl Cl2. It's an easy compound, there is no exception or something. Yeah, I want everyone to give the answer for this coordination compound. Students, please go through it and let me know the answer for it. You can unmute and say, that's enough.
Tetramine aqua.
Tetramine amine. Okay, aqua. Then tetramine aqua. Name is over. Only this much name. Yeah, anyone can answer. Tetramine aqua. Then what about this one? This is chlorine. Whenever chlorine is a negative ligand or anionic ligand. So when it's coming into the nomenclature, what will be the name? Chlorine. Yeah, chlorido. That is, E will be replaced by O. E will be replaced by O in the case of anionic ligand.
Cobalt 3.
Yeah, next one is cobalt. And oxidation. Cobalt 3 or 2? Cobalt 2, are you sure? 3, because 3 chlorine are there. 3 chlorine means the primary valence itself is coming 3. So cobalt 3. Then chloride. Very good, excellent. Yes, hope all of you got a complete understanding about nomenclature. All of you try some different compounds and get a complete idea about nomenclature. These are some different compounds I have taken to get an understanding of nomenclature. Okay, shall I move to the next topic, that is effective atomic number? Shall I move? Yes, thank you. Yeah, effective atomic number. Effective atomic number will be telling you the stability of coordination complex. How it is telling the stability of coordination complex, that I will be explaining now. Okay, listen here students. How we will be doing it? First of all, we will be finding EAN number, effective atomic number. How we can find it out? It is atomic number minus oxidation state plus 2 into coordination number plus 2 into coordination number plus 2 into coordination number. Okay, all of you know, right, what is coordination number? What is coordination number? I think I didn't say that one in the basic, but I hope all of you know what is coordination number. It is a number of, what it is? It is a number of sigma bonds attached to the metal atom, or number of donor atom attached by ligands to the central metal atom. Okay, now I am giving you some examples. Before going to some examples, I will be telling you how effective atomic number will be explaining the stability. If EAN number, if EAN number follows noble gas number, noble gas atomic number, noble gas atomic number like 18, 36, 54, 86, then they are stable, and we can say the compound is obeying EAN rule. I can give an example. CuNH3 4 SO4, CuNH3 4 SO4. Find out the EAN number of this compound and tell me whether it is following EAN rule or not. Yes. What is the atomic number of copper? 29 atomic number minus. What is the oxidation state of this compound? What is the oxidation state of this compound? Tell me, guys. What is the oxidation state of this compound? No. Okay, yeah, the answer is yeah, correct only. It is not following EAN rule. But I want the EAN number. What is the EAN number of this one? 29 minus oxidation state. It is 2. Because sulfur SO4 2 minus. What is oxidation of sulfur? Sulfate. 29 minus 2. Then plus 2 into coordination number. What is the coordination number? You can see it is 4. So what is the answer you will be getting? You will be getting 35, which means it is not obeying EAN rule. But there can be one more question from this part. What is that question? Question can ask whether this compound can act as oxidizing agent or reducing agent. Whether this compound can act as oxidizing agent or reducing agent. What is the answer going to be? See here yeah, very good. Here 35, right? 35 is EAN number, which means it need one more electron. If it need one more electron means it will be accepting one electron, which means it undergoes reduction. If it undergoes reduction, it will be acting as oxidizing agent. Yes, very good. That is the one point you have to note down here. If the EAN number is just above the noble gas atomic number, then they will be undergoing oxidation by losing electron and will be acting as reducing agent. But if the EAN number is just below the atomic number of noble gas, then they will be gaining one electron and they will be undergoing oxidation and they will be undergoing reduction and will act as oxidizing agent. That's another point you have to note down here. Shall I move, students? Yes. One more example I can give you and you can tell me whether it is following EAN rule or not. K4 FeCN6. Find out whether it is following EAN rule or not. Atomic number of iron. What is the atomic number of iron? 26. Yes, very good, Kiran. It is following EAN number. What is the EAN number here? 26 minus oxide state 2 plus 2 into 6. What is the answer? Coming as 36. Yes, very good. So this is how you have to check the EAN number and thereby you can understand the stability of it. Yes. So that's all about EAN number. Yeah. Have you all noted down all the points? Everything done? Just note down the equation. Don't forget this equation to find out the EAN number. Okay, moving to the next one. Next one is about Vernier coordination theory. Actually, this is one of the first theory or one of the primary theory that is used to explain the coordination compound. That is Vernier theory. It's very simple. According to Vernier theory, there are two types of valencies are there. One is primary valency and another one is secondary valency. What is primary valency? It is just the number of oxidation state. What is the oxidation state of a compound? That is what primary valency. And this primary valency, the ligand which is satisfying this primary valency are ionizable. They are ionizable. Okay. Now coming to secondary valency. What is secondary valency? Secondary valency is nothing but just count the coordination number. Just find out the coordination number of it. That is a secondary valency. And they are non-ionizable. They are non-ionizable. Why they are non-ionizable? Because it will be inside the coordination sphere. As it is inside the coordination sphere, it is very stable. It can't be broken. Okay. Yes. I will be just giving an understanding by taking an example. CONH3 6, CONH3 6, Cl3. What is the primary valency and secondary valency of it? What is the primary valency and secondary valency of this compound? Primary valency is what? What is the primary valency? Yes, excellent. It is 3. What is the oxidation state of this copper? X minus 3 is equal to 0. That is X is equal to plus 3. What is the oxidation state? That is the primary valency. What about the secondary valency? What about the secondary valency? Yes, very good. It is 6. Secondary valency is number of coordination number. It's a coordination number only. 6 coordination numbers are there. 6 sigma bonds are forming to the central metal atom. Okay. So we got primary valency and secondary valency. It's a very easy thing. And what is the problem here is this primary valency is ionizable. How we can verify that it is ionizable? If I add water to it, what you can see is you will be getting CONH3 6 3 plus 3 Cl minus, which means you got total 4 ions in water. You will be getting 4 ions in water, and here we can this Cl, chlorine will be dissociated and you will be getting 3 chloride ions, and the ligands or the things that is inside the coordination sphere is not broken, and because they are stable, and that is why here we can see this 3 primary valency 3 is satisfied by chlorine, right, and they are ionized in the water. So we will be calling it as ionizable valency. And the valency, secondary valency, that is coordination number, they are not ionizable. They haven't split into its ions, so that is why they are non-ionizable. Okay, this is the understanding of primary valency and secondary valency. Now one of the applications I can give you related to the primary valency and secondary valency. Are you done, students? It's a very easy thing only. Just go through the oxidation number, you will get primary valency, then secondary valency, you will get it from the coordination number. Can I move? Are you there, students? Okay. Just give me some examples. I will be giving a question. Arrange the following in the order of electrical conductivity. Order of electrical conductivity. Arrange the following in the order of electrical conductivity. Okay, option first option is CONH3 6 Cl3. Second one is CONH3 5 Cl2, and third one is CONH3 4 Cl2 Cl. 1, 2, 3. Which is having more conductivity? Go through it. Let me know the answer in the chat box. Yes, 1, 2, 3. Yes, excellent, Kiran. 1, 2, 3. Yes. How we can check the electrical conductivity? Electrical conductivity is directly proportional to the number of ions present in the solution. Here you can see how many ions it will be forming. How many ions? Already we have discussed. They will be splitting into 1 plus 3, that is 4 ions. And here you can see how much ions will be forming. the ions, that is the ligand that is present inside the coordinate sphere, won't be splitting, so they will be existing as a single ion. So 1 plus and 2 chlorine outside, only the ligand or only the counter ion which is outside the coordination sphere only will be splitting, and they only will be involving in the reaction. Okay, and 2, which will be 3 ions, and here 1 plus 1, it is 2 ion. So order of number of ion is higher for the first one, then second one 3. Yes, very good. So this is one of the application you can see in the case of Vernier theory. Go through it, everyone. Okay. Yes, Vernier theory is over. Now we will be moving into the next theory, that is valence bond theory, another important one. Shall I move, students? Have you all got the idea? Yes. Now the valence bond theory. Valence bond theory, I am not going into the theory or the points of it, because that is not required. Only according to the exam point of view, this is the point that you have to note down. If the coordination number is 4, then there can be two type of hybridization. It can be either sp3 hybridization or it can be dsp2 hybridization. Remember that if the hybridization is sp3, the geometry is tetrahedral, and if the hybridization is dsp2, it will be square planar always. And remember that coordination number 6 also can have two hybridization. First one is sp3d2, then d2 sp3, and in both these cases the geometry is same. The geometry is same in both the different hybridization of octahedral complex. Then what will be the difference? If it is sp3d2 hybridization, it will be outer orbital complex, that is outer d electrons only, outer d orbitals only will be involved in this mixing. In the case of d2 sp3, the inner d orbitals only involved in the mixing, so they will be inner orbital complex. So this is the point that you have to note down. Now we will be finding the hybridization, and thereby we can easily find out the geometry. Got it students? Moving. Yes, I am just giving you a few examples. Find out the geometry and hybridization of the following, and some exceptions also there, that also I will be adding it. Find the geometry and hybridization. First one, CO NH3 6 3 plus. Okay, first of all, find out for this one. Okay, how will be? First, I will be giving an example how we can find out the geometry. For finding geometry, we should find out hybridization first. For finding the hybridization, you should know what is oxide state of cobalt here. Here the cobalt is existing in +3 oxide state. It is D6 complex, and D6 it will be in the absence of ligand 1, 2, 3, 4, 5, 6. In the absence of ligand, the number of d electrons will be placed according to the Hund's rule. Now in the presence of ligand, that is CONH3 6, CONH3 plus 6. In the presence of ligand, what is going to happen is NH3 is a strong field ligand. How we can understand whether it is a strong field ligand or weak field ligand? We will be going through the spectrochemical series of it after this, then we can understand that one. For time being, just understand that ligand which is having nitrogen and carbon as a donor atom, they are strong field ligand. Ligand in which nitrogen and carbon are the donor atom, they are strong field ligand. Okay, now as they are strong field ligand, they will be doing the pairing. As how they will be doing the pairing? 1, 2, 3, 4, 5, 6. They will be doing the pairing. Okay, now there will be, this is 3D, then this is 4s, then 4p orbitals. Now how many orbitals we need? There are 6 ligands are there, so we need 6 vacant d orbitals, not d orbitals. So we need 6 orbitals to accommodate the NH3. So what I will be taking? I will be taking these d2 and 3 p orbitals and 1 s orbital. So d2 sp3 is the hybridization of this particular complex. D2 sp3 is the hybridization of this particular complex. And if it is D2 sp3, what is the geometry? What is the geometry if it is D2 sp3? Yes, very good, it is octahedral. Yes, good, octahedral. And it is inner orbital complex or outer orbital complex? Inner or outer?
Inner.
Yes, very good, it is inner orbital complex. And my question is, there is 2 d orbital involving in the mixing, right? Do you know which are the 2 d orbitals that will be involving in D2 sp3 hybridization? We know there are 5 d orbitals are there. In that, which 2 d orbitals will be involving here? That is dx square minus y square and dz square. That is, axial d orbital will be first involved in the hybridization, then only the non-axial d orbital will be involving. Okay, these are the points I want to add in this part. I will be giving few more questions. Some exceptions are there. That is the main point. This I know you all know how to do all these things. Now we can go through some of the exceptions. That is a point you had note down in your notebook. Yes. CO NH3 6 2 plus. CO, sorry, not CO, it is CU. CU NH3 6 2 plus. What is the hybridization of this one? What is the hybridization? First of all, copper is in 2 plus, copper is in 2 plus oxide state, and it is D9 complex. How the D9 complex will be arranged? 4 5, okay, 4s 4p. Okay, yeah, 1 2 3 4 5 6 7 8 9. Okay, there is one unpaired electron we can see here. Okay, now in the presence of ligand Cu NH3, in the presence of ligand also you can see there is same only, there is no different arrangement. But here how we can find out the hybridization? What is the hybridization for this one? What is the hybridization that you are expecting here? What is the hybridization you are expecting here? sp3 d2. That is the hybridization that you are expecting, that is 1s 3p and 2d will be using here. But actually the hybridization here is not sp3 d2, it will be d2 sp3. Sorry, 1 minute. Sorry, it is not octahedral complex, it is a tetrahedral complex. That is what the exception. 4 only, sorry. Yeah, it is 4. If it is 4, then what is the hybridization that you are expecting? What is the hybridization? What is the sp3 is the hybridization that you are expecting. Okay, but what is actually going to happen is, theoretically it has been found that this complex is having square planar geometry. This complex is having square planar geometry. If it is square planar geometry, then what would be the hybridization? What would be the hybridization? Square planar. What is the hybridization? DSP2, very good. But how we can explain that one? For that we are just using a theoretical way of explanation. That is, we will be jumping this electron. We will be jumping this electron to the one of the p orbital, and then we will be taking this d orbital. Then we will be taking this d orbital and one s orbital, and among the 3 p orbital 2 we will be using. And so finally we will be explaining the experimental fact that it is dsp2 hybridization. dsp2 hybridization. So note down, this is one of the exception in the VBT theory, and it is having square planar geometry. Okay, now one more thing is there, that is Mn Cn 6 3 minus. What is the hybridization for this one? What is the hybridization? Have you understood the second one, which is exception? Just note down this complex, D9 complex. What is the hybridization and geometry of this one? MnCN 6 3 minus. Here manganese is in what? Manganese is in plus 3 oxide state. Plus 3 oxide state means what? It is D5 complex. D5 complex means, yeah, D5 complex. (3D) 4S 4P. Yeah, in the absence of ligand, sorry, it is not D5. What is the number? It is D4. 1 2 3 4. Okay, now we know that Cn is, what is Cn? Cn is a strong field ligand, right? Cn is a strong field ligand. It will do the pairing. So in presence of the ligand, it will be doing the pairing. And how the pairing will be taking place? 1 2, then this, what is this? Can I do this type of pairing? If I do this type of pairing, what is the hybridization? What is the hybridization? We need 6 vacant orbitals. We need, yeah, actually here you can see there are 3 vacant orbitals are there. 3 vacant orbitals are there. Can I write the hybridization is 3 D3 sp D3sp2? Can I write the hybridization? There is no hybridization as D3sp2. So what I will be doing is, I won't be pairing one of the orbital. What I will be doing, I will be unpairing this one. I will be unpairing this one, and will be keeping the 2 electrons unpaired, remaining paired, and resulting we will be getting D2sp3. Because for doing the hybridization we need only 2 d orbitals. We don't need 3 d orbitals. So what I will be doing is, 2 electrons will be remains unpaired there. 2 electrons will be there, remains unpaired, and because of this we can say this is going to be a paramagnetic species. Okay, so these are some of the exceptions in the valence bond theory, in which you have to note down and don't lose any mark from this part. Remaining everything is same according to the valence bond theory rule. Is it clear, everyone? Shall we move to the next one? That is the major one, the mega one. What it is? Crystal field theory. Yes. But before going to the crystal field theory, I want all of you to take a note of spectrochemical series, pairing, strong field ligand, weak field ligand. What all these things? Okay, spectrochemical series, it is in which ligands are arranged according to the increasing order of their strength, or increasing order of their splitting energy. Okay, based on that we can classify ligands into strong field ligand and weak field ligand. What are strong field ligand? They will be leading to large splitting. They will be leading to the large splitting of d orbitals. We know that d orbitals, they are axial d orbital and non-axial d orbital, and in the presence of ligand they will be splitting into 2, axial and non-axial. And strong field ligand will create a large splitting gap. And in that case delta O will be greater than pairing energy. And in this case the electrons will be remain paired in the lower orbital. So whenever there is a strong field ligand on the central metal atom, there will be low spin complex, because all the electrons will be paired in the lower orbitals. Now in the case of weak field ligand, their splitting energy will be very less. And as their splitting energy is less, they will be remain unpaired. As they remains unpaired, you can see it will be forming high spin complex. The spin will be higher because it is weak field. Okay, now next one is halide donors. They form high spin complex. All the halogens will be acting as a weak field ligand, and all the oxygen donors also will be acting as a weak field ligand. And which are the strong field ligands? How we can understand that? The following are strong field ligand. If nitrogen and carbon is coming as the donor atom, then they are strong field ligand. If oxygen, halogen and sulfur, if these things are coming as the donor atom, then they are weak field ligand. Okay, now I will be giving you the spectrochemical series, and I will be telling you how we can understand how to remember these things. Okay, this is the spectrochemical series. Just look into it. Here you can see the lowest splitting energy is for iodine. Okay, iodine, then bromine. I am writing it as halogen. Okay, then comes sulfur, then HCN also having sulfur is a donor atom. So then comes sulfur, then comes chlorine, then comes fluorine. It's not following the direct order. In between sulfur is also coming. Then comes what? Then comes oxygen donor, OH minus. Oxalate is also oxygen donor. H2O is also oxygen donor. Then the strong field will be coming for the ligand which is having oxygen is a donor atom. Okay. Then comes, you can see NCS having nitrogen is a donor atom. EDT also nitrogen is a donor atom. NH3 nitrogen is a donor atom. Ethylene diamine also nitrogen is a donor atom. NO2 also nitrogen is a donor atom. So next coming the ligand with the nitrogen is a donor atom as the strong field ligand. Then comes cyanide and carbon monoxide. Both are having carbon is the donor atom. Carbon is a donor atom. This is the easiest trick that you can follow to understand the strength of the ligand. That is, first one is halogen, that is iodine and bromine, then sulfur. Halogen, then sulfur, then only chlorine and fluorine will be coming. Chlorine and fluorine is coming in between sulfur and oxygen donor. And then nitrogen, then carbon. These two are strong field ligand. Remaining all are weak field ligand. But here you can see oxygen. Oxygen is coming actually in the middle. It will be having a moderate field ligand. Oxygen in some cases means if the metal is having higher oxide state, in that cases you can see oxygen donating ligands, that is C2O for oxalate and H2O. They will be acting as a strong field ligand. That's the point you have noted down for the oxygen. Example, cobalt H2O6, CO H2O6 3+, in which H2O will be acting as a weak strong field in that. Okay. So these are the crystal field theory spectrochemical series. Now we can move into the crystal field theory and how the splitting is taking place. Got it, everyone? Have you understood how the splitting is taking place? Not splitting, how the order is arranged. Okay. Just follow this. If you are not able to remember the complete series, just follow this one. You can easily identify which is strong field and which is weak field. Okay, now coming into the crystal field theory. According to crystal field theory, if you observe, you can see it will be treating the metal ion and ligand as purely electrostatic force of attraction. And what is going to happen? In the presence of ligand, there will be splitting of d orbital taking place. That is, initially in the absence of ligand, the 5d orbital will be in the ground level. And first of all, I am talking about octahedral splitting. Octahedral splitting, 5d orbital. Now in the presence of ligand, or when the ligand start approaching from a distance to the central metal atom, all the d orbital will be togetherly raising its energy. Got it? And after this, what is going to happen? When it comes little more closer to the ligand, this d orbital will start splitting into 2d orbital. That is, this is dxy, dyz and dxz. This is dx square minus y square. This is dz square. And this dxy, dyz, dxz. This will be togetherly calling it as T2g orbital, and dx square minus y square dz square will be togetherly calling it as Eg orbital. And the g term is representing the symmetry, that is geroid. Okay, got it? This is how the octahedral splitting is taking place. And now you can see why the Eg orbital is having higher energy. It is because the ligand is approaching along the axis of the d orbital, So the orbital which are dying along the axis, that is dx square minus y square and dz square, they will be raised in energy and will be having a higher energy. Okay, and how much it is raised, that much which will be remaining d orbital will be lowered. This is about octahedral splitting. Now what about tetrahedral? Tetrahedral also same thing. Initially they will be lower energy, then when ligand approaches, all of the d orbital will be raised in energy all of a sudden, then it will be start splitting when the ligand approaches little more closer. But here in the case of tetrahedral splitting, the splitting is taking place in such a way that the non-axial d orbital, that is T2g orbital, dxy, dyz, dxz, that is T2g orbital, and here it is not mentioned as T2g, it is T2 only. They will be higher in energy, and the EG orbital, dx square minus y square, dx square minus y square and dz square, that is EG orbital, E orbital. They will be lowered in energy. In the case of tetrahedral splitting. Why? In the case of tetrahedral splitting, the ligand is approaching along the not along the axis, it is in between the axis. Ligand is approaching in between the axis. So orbitals which are lying in between the axis, that is dxy, dyz, dxz, they will be raised in energy. Okay, and the remaining will be lowered in energy. And we won't be using G term here. G is using whenever there is a symmetry. In the case of tetrahedral complex, there is no symmetry, so we will be cancelling out the G term here. Okay, this is how octahedral splitting and tetrahedral splitting will be taking place. Now we can go into the equation how we can calculate the CFSE, crystal field stabilization energy of octahedral. It will be equal to number of electrons in T2g orbital into minus of 0.4 plus number of electrons in EG orbital into 0.6. This is how we can calculate the crystal field stabilization energy of octahedral complexes. Now in the case of tetrahedral, it is represented crystal field stabilization energy, it is equal to number of electrons in E orbital into 0.6 minus 0.6 plus number of electrons in T into 0.4. Okay, this is how we can find out the CFSE of octahedral splitting and tetrahedral splitting. Just go through the equation, everyone. Okay, got it, everyone? Why we are calculating CFSE? CFSE is having a lot of application. Higher the magnitude of CFSE, more stable the compound is. Okay, there is one more point you have to add on in the equation, that is plus NP. What is NP? NP is a number of pairing that is caused due to ligand. It is the additional or extra pair that has come due to ligand. That also you have to add here, plus NP. Okay, higher the magnitude of CFSE, more stable the complex. Normally CFSE is that stability of a complex is directly proportional to CFSE, and also it is directly proportional to the chelation or chelate formation. So this is a summary of octahedral splitting and tetrahedral splitting. Now we can move into some of the applications, some of the points, some of the characteristics of CFSE. Okay, shall we move, students? Have you noted down the difference between tetrahedral and octahedral? And note down that tetrahedral splitting is very less. The splitting gap of tetrahedral, the splitting gap of tetrahedral is very less, in which all the ligands will act as weak field ligand. The splitting gap of tetrahedral complex is very less, in which all the ligand will be acting as a weak field ligand in the case of tetrahedral. Okay, NP is the number of pairing. I will be giving an example and I will be telling you how we can find out the number of pairing. It is extra pairing that is caused due to ligand. Just wait, when I am going into the magnetic property, I will be giving you the example and thereby you can understand it. Okay. Now splitting up of tetrahedral is very less comparing to the splitting up of octahedral, and thereby because of that ligand will be acting as a weak field ligand in the case of tetrahedral. And if I am just comparing tetrahedral splitting and octahedral splitting, tetrahedral splitting is equal to 4/9 of octahedral splitting. Tetrahedral splitting is 4/9 of octahedral splitting. Okay, that's one more point. Now another point is if the central metal atom belongs to 4D and 5D series, if the central metal atom belongs to 4D and 5D series, then all the ligands will act as strong field ligand. In the central metal atom, if it is 3D series, then only you have to go for the weak field ligand and strong field ligand. If it is not belongs to 3D series but belongs to the 4D and 5D series, then all the ligands, no matter whether it is strong field or weak field, all will be doing the pairing. Okay. Now another point is higher the oxidation state of central metal atom, higher the oxidation state of central metal atom, higher the CFSE. If the central metal atom belongs to the higher oxidation state, example I can give CrH2O 6 2 plus first compound and CrH2O 6 3 plus. In this case which is having the highest CFSE, all are having same ligand, both are having same ligand. How we can compare the stability of both, which is more stable, Cr2 plus or Cr3 plus? Give me the answer. What I mentioned, higher the oxidation state of central metal atom, higher the CFSE or higher the stability. Which one? Guys, are you there or you guys are sleeping? Yes, very good. Cr3 plus is more stable. Higher the oxidation state, higher will be the stable. So remember, note down Cr3 plus. This H2O6, here H2O acts as a strong field ligand. Here H2O act as a strong field ligand. Not only this one, cobalt H2O 6 3 plus, then CO H2O CO oxalate 3. Oxalate is a bidental ligand 3 plus. In all these cases H2O ligand act as strong field. This is clearly mentioned in the NCERT. Note down, this is mentioned in the NCERT. That is why I am adding here, because NCERT things are having high probability to ask in NEET exam. So just note down these things. Okay. Yeah. Are you clear, students? Okay. Now we can move into the magnetic properties. Shall I move? Have you noted down all the points regarding the crystal field and octahedral splitting? Yes, thank you. We'll be moving into the CFSE calculation. Already we have done the equations. Now we'll be moving into the magnetic property. When it's coming to the magnetic property, you have to follow which one? You have to follow crystal field theory. You should not follow valence bond theory. You might be getting wrong answer if you follow valence bond theory. So how we can calculate? just find out the number of unpaired electrons and use the equation. This equation is there everywhere in atomic structure chapter also. In many chapters you can see this equation, root of n into n plus 2. What is n? N is the number of unpaired electron. We can go through some examples and thereby we can get a clarity. Yeah, first one, find out the magnetic moment of the following and CFSE also. Find the magnetic moment and CFSE. First one, K for Fe Cn K for FeCN 6. K for FeCN 6. Find out the magnetic moment and CFSE. How we can solve this? First of all, understand the oxide state of Fe. Here Fe is in +2 oxide state, and here you know that Cn is strong field. As it is strong field, and here it is octahedral splitting. So how the splitting will be taking place? 1, 2, 3, 4, 5. Yeah, and Fe2 plus it is D6 complex. So initially 1, 2, 3, 4, 5 and 6. Before the coming of ligand, this will be the order of electrons in the d orbital. That is, it is following Hund's rule. Now what is going to happen when ligand approaches? That is Cn approaches, it will be splitting into T2g and Eg. T2g. Okay, and as it is a strong field ligand, what is going to happen? There will be higher splitting gap, so the filling will be, first will be half filling everything 1, 2, 3. Then it can't go to the higher level because splitting energy is very higher. It will be paired in the lower one. Okay, now we can find out the CFSE. How to calculate the CFSE? Number of electrons in T2g plus number of electrons in n into number of electrons in T2g into minus 0.4 plus number of electrons in Eg into 0.6. So how many electrons are in T2g? 6 electrons are there. 6 into minus 0.4. What is the CFSE value? Minus 2.4. We got the CFSE value minus 2.4 plus number of pairing. What is the number of pairing here? Yeah, very good. It is diamagnetic. Very good, because there is no unpaired electron. Now you understood that there is no unpaired electron here, and so it is diamagnetic. Okay, now what about this one? What is the number of unpaired? What is the NP value here? Someone has asked what is NP. Here you can see before splitting how many unpaired electrons are there. There is one unpaired electron. After the splitting you can see extra 2 more pair electrons also came, right? Which means that is the number of pairing energy, that is 2p. That is extra pairing caused due to splitting. It is not 3. There are 3 pairs are there. That is not the number. It is 2 only. 2p. Got it? Number of pairing. Now unpaired electron, n value is equal to 0. So magnetic moment value nu is equal to 0. So it is diamagnetic. Understood everyone? Is it clear completely to you? Okay, yes, thank you. Shall I give you one more example? One more example I can give you. K for FeCl 6. K for FeCl 6. Find out the CFSE value and magnetic moment. Here also Fe is in +2 oxide state, and we know that chlorine, it is a weak field ligand. Chlorine is a weak field ligand. As it is weak field ligand, initially it is having 1, 2, 3, 4, 5, 6. And how the arrangement of electrons? As it is a weak field ligand, the splitting energy is very less. After third electron, the next electron, fourth electron will be goes to the higher level, then comes to the lower level and will be paired there. Got it? It will be following Hund's rule. Clear? Now what is the CFSE? Number of electrons in T2G. Number of electrons in T2G, that is 4 into minus 0.6 plus 2 into what? 2 into 0.4. What is this value coming? What is this value coming? Minus 0.4. See here you can see when I am comparing the strong field ligand and weak field ligand. Yes, very good. Now you can see number of unpaired electron, n value is equal to 4, and so the new value is equal to root of n into n plus 2. And what is n value? Root of 4 into 6. It is the root of 24. Root of 24, we all know that it will be just below the 5. Root of 25 is 5, so root of 24 is 4.90 something, Bohr magneto. Very easy question. Now you can see both above case also we have done Fe2 plus only, same number of electron, and here also same number of electron D6. But among these two, which is more stable? Which is going to be more stable? Strong field ligand or weak field ligand? Strong field ligand or weak field? Just check which is having highest magnitude of CFSE. In the previous cases you can see the magnitude of CFSE is minus 2.4. Magnitude is coming 2.4. Second case it is coming just 0.4 only. So which is having highest CFSE or which is more stable? The one which is strong ligand is more stable. The one which is strong field ligand is more stable. So some cases if the CFSE will be same, some cases there will be same CFSE. If the CFSE is same, then the complex with a strong field ligand is more stable. If the CFS is same, then the complex with a strong field ligand is more stable. That you can just note it down. Is it clear, everyone? Shall we move to the next topic? Next two more topics are there that we will be covering it. Yes. Yeah, next topic is metal carbonate. It's a very easy type of topic because we already covered this one where in the paper discussion time. Metal carbonate, the synergic bonding. Yeah, what is this one? This is explaining the strength of metal carbonyl bond. That is, we know that metal is having vacant d orbital, right? Okay, metal is having vacant d orbitals. Okay, and the carbon monoxide we know that it is having carbon oxygen and there will be lone pair on the oxygen. What is going to happen? First of all, this lone pair will be donating electron to the vacant d orbital. It will be donating electron to the vacant d orbital of the metal and will be forming a sigma bond. Note down, it will be forming sigma bond. Then what is going to happen? When the metal become electron rich, when electrons are donated to the metal will become electron rich. Once the metal become electron rich, the electrons in the metal will be back donating to the anti-bonding pi star orbital of the carbon. Anti-bonding pi star orbital of the carbon and forming a sigma bond. First it will be and will be forming a pi bond. First it will be forming sigma bond, then metal will be back donating electrons to the anti-bonding pi star orbital of carbon and will be forming a sigma bond. Okay, thereby the metal carbon bond strength will increases. That is what? Back bonding. Okay, this process is called as back bonding, sigma and pi bond. So as back bonding increases, if back bond increases, what is happening? Metal carbon bond strength increases. If metal carbon bond strength increases, what is going to happen to the carbon oxygen bond strength? Will it increase or will it decreases? If this one will be more closer or stronger, what is happening to the carbon and oxygen? Carbon oxygen bond strength will decreases. Carbon oxygen bond strength decreases. Okay. Now one more question can ask, that is about the stretching frequency of carbon oxygen. Stretching frequency of carbon, that is nu CO. If the carbon oxygen bond strength decreases, stretching frequency of carbon oxygen also will be decreasing. Nu CO is the stretching frequency. What is stretching frequency? It is the energy required to stretch the carbon oxygen bond. That is what stretching frequency. If the bond strength is lesser, we need only less energy to stretch the carbon oxygen bond. These are the points that you have note down in the case of metal carbonyl complexes. Now how we can increase the back bonding? Back bonding, yeah, if the negative charge on metal increases, back bonding also increases. This is the only point that you have note down in the case of synergic bonding or synergic effect. Back bonding increases, metal carbon bond strength increases, then carbon oxygen bond strength decreases and stretching frequency decreases, and just opposite to the bond length. This is bond strength, and we all know that it is all these are just opposite to the bond length. Clear? Can I give you one small example? After that we can move into the last part, that is isomerism. Shall I move, students? Have you understood this one? Yes. Need the response? Yes. Okay. I am just giving a small example. Arrange them based on the back bonding. Arrange them based on the back bonding. First one is CrCO6, then second one VCO6 minus, the third one is MnCO6 plus. What is the order? What is the order of back bonding? What is the order of back bonding? 1, 2, 3. Back bonding, I said back bonding will increase if the ligand is, if the metal is having negative charge. So which among these having negative charge on the metal? Second one. Then comes a neutral one, that is first one. Then comes the last one. So higher the negative charge on the, very good Surabhi. Higher the negative charge on the metal, higher will be the strength, higher will be the back bonding, and higher will be the strength of metal carbon. Lower will be the strength of carbon oxygen. Yes, that's the point you have noted down in the case of synergic bonding. Okay, now we'll be moving into the next topic, that is what isomerism. Isomerism, it is two types. First one is structural isomerism. Structural isomerism, I think that is very easy for you. Yeah, there are four types of structural isomerism. Linkage isomerism, where you can see linkage isomerism, where you can see, we can see the linkage isomerism if there is an ambidentate ligand. If you see NO2, if you see SCN, NCS, or if you see CN or NC, in those cases the compound will be forming, or compound will be having linkage isomerism. Example CONH3,5NO2, in which the ligand can bind to the metal atom by any of its donor site. Okay. Now ionization isomerism. If you see coordination compounds, in which there will be counter ion, there will be exchange of counter ion and the ligand. In those cases you can say that is ionization isomerism. Exchange of counter ion with the ligand. Here you can see SO4 and Br, and they have exchange. Br comes inside the coordination sphere, Br SO4. So these type of compound are called as ionization isomerism. Then coordination isomerism. For forming coordination isomerism, what is the primary thing? There should be two coordination sphere. And there should be exchange of ligand between the cationic and anionic entities. This is cationic entity and this is anionic entity. Left side will be cation, right side will be anion. If there is an exchange of ligand between these two, that will be coordination isomers. And last one, solvate isomerism or hydrate isomerism. Solvate or hydrate isomerism means there should be water. There should be water as a ligand, and also there should be water as a crystallization also. There should be water molecule should act either as ligand. Here the water molecule is acting as ligand, and here the second case the water molecule is acting as a water of crystallization. So in all these cases we can say the compound will be having solvate isomerism. It is very easy to identify what is which one is showing linkage, which one is showing coordinate, which is solvate. Very easy only, there is no problem. The problem comes in the stereoisomerism. Are you clear, students? Shall we move to the stereoisomerism? Yes. Coming to the stereoisomerism. Okay, stereoisomerism, it is of two types, geometrical isomerism and optical isomerism. Okay, in the case of geometrical isomerism, there will be cis-trans and facial or meridional isomerism. Facial and meridional isomerism I am not going to discuss because I already discussed this one in the mock paper discussion. I will be discussing about geometrical isomerism and also optical isomerism. I will be telling you the easy trick how you can score from this part in the exam. Okay, just go through it. First of all, stereoisomerism. It is geometrical isomerism and optical isomerism. Isomerism. That is, if I am asking you number of isomers, it is sum of optical isomers and geometrical isomers. I will tell you a trick how you can easily find out the answer. First of all, I am going with the coordinate number 4. Coordinate number 4. If the coordinate number is 4, it can be either tetrahedral as well as square planar. In the case of tetrahedral, if you can see, this is what tetrahedral. It can be anything. It can be A, B, C, D. In the case of tetrahedral, you can see the bond angle is 109.5 degree. Everywhere the bond angle is 109.5 degree. If I change the position of any of these two, if I change the position of the ligand of any of the things, there is no change in the bond angle between the ligands, which is changed. So in this case, there is no geometrical isomerism. Tetrahedral complexes won't be showing geometrical isomerism because there is no change in the bond angle. Geometrical isomerism will be shows if there is a bond angle difference. Okay. Now what about optical activity? Which type of compound? MABCD. MABCD will be optically active. In the case of tetrahedral complexes, MABCD type complex will be optically active, because if I am taking MABCD complex, there won't be any plane of symmetry. How we can say whether a compound is optically active or inactive? If there is no plane of symmetry, it is optically active. If there is a plane of symmetry, it is optically inactive. Here we can see MABCD type of complex. If I am cutting along these two axes, I will be getting two different plane. I will be getting two different parts in which there is no plane of symmetry. So MABCD type complex is optically inactive. Yes, coordinate number 4 with the tetrahedral is over. That's only. Now for square planar. For square planar, they will be shows geometrical isomerism. They will be showing geometrical isomerism. Look at here. Listen carefully. Okay. It is of different type. MA4, then MA3B, then MA2B2, then MABCD. These are different type of square planar complex. Now among these, how many geometrical isomerism it is having and how many optical isomerism it is having? How we can understand that one? Just follow this rule, this trick. If how many combinations are possible that much geometrical isomers are there. That is MA4. How many different ways I can arrange MA4? That much will be the number of geometrical isomers. Don't worry, I will be giving you example. Please patiently wait. Okay. Now how we can find out how many optically active compounds are there? If any of the pair have same ligand, that is AA. If any of this pair is having two same ligand, AA, or if any two pair like AB are same, then the compound is then the complex is optically inactive. Then the complex is optically inactive. This is the trick that you can follow to find out number of geometrical isomers and number of optical isomers. I will be giving an example. Which example I can take? Here? Okay, I am taking example of, which example you want, guys? MA2B2 example I am taking. Look at here. In the case of MA2B2, what are the different ways I can arrange this one? One is MAA one combination, then MBB another combination, then any other combination, MAB, then AB. Any more combinations are possible? Tell me, guys, any more combinations are possible? No, right? Yes or no? Are you there? Any more combinations are possible? No. Which means how many combinations are possible? 2 combinations are possible, and so 2 geometrical isomer. We have 2 geometrical isomer. Okay. 2 combinations. So 2 geometrical isomers. Now among these 2, which are the optically active and which are the optically inactive? How we will be understanding that one? I said if any of the pair is having same ligand. See here you can see in the first geometrical isomer, it will be cis. In that you can see these 2 in this pair having 2 same ligand. If there is a pair with 2 same ligand, then they will be optically inactive. And here you can see, there is no pair with the same ligand, but there are pairs with the same. There are 2 pairs which are same. So in this case also optically inactive. And thereby you can see there are 2 geometrical isomers plus 0 optical isomers. So if I am asking what is the number of stereoisomer? What is the number of stereoisomer? Students? Tell me. 2 plus 0, it is equal to 2. This is how easily you can find out how many geometrical isomer is there and how many optical isomer is there. And remember that square planar complex are not optically active. Why? Because they always, any square planar complex have a square planar symmetry. If I can cut along the horizontal axis and I will be getting 2 equal parts, which means it is optically inactive. Okay, now I will be winding up with one example of coordination number 6. I am just taking a random combination of ligand. Coordination number 6. I am just taking okay, MA3BCD type of complex. You have to tell me how many geometrical isomers are there and how many optical isomers are there and what is the total stereoisomer. That is my question to you. If you understood this trick, you can easily find out the answer for this. Just tell me, guys. Tell me how many combinations are there. MA3BCD. I know all of your math students asking number of combinations and permutations are not good to you. But still we need. Okay, how many combinations are there? First combination, it is octahedral, so there will be 3 pairs. First pair is MAA, then AB, then CD. This is one pair. What is another pair? MAA, then AC, then BD. Any other pair is possible? MAB, AC, then AD. Any more pair is possible? Check it. MAA, then AD, then BC. How many pairs are possible or how many combinations are possible? Any more combinations are possible? Tell me, guys, I need answer from you. Are you all doing it? Easily you can score if you understood this one trick. Just find out the combinations. Any more? Any more is possible or not? No, there is no more combinations possible. So how many geometrical isomer? How many geometrical isomer? My question is to you. How many geometrical isomer? How many combinations? 4. Very good. 4. And among these, which are optically active, which are optically inactive? First one, optically inactive or not? First one, is it optically active or not? Here you can, there is a pair with two same ligand. There is a pair with two same ligand. So of course it is optically inactive. Oh, I am writing optically inactive. Now second one, here also there is a pair with the same ligand. That is also optically inactive. Now here option 3, MAB, MAC, MAD. Is it optically active or inactive? Tell me. Tell me guys. Optically active. Very good. Optically active. Here there is no ligand which is same in a pair, and there is no pair which are same. So it is optically active. Now coming to the last one. Yeah, AA, optically inactive. So what is the total stereoisomer? Optical isomers are is equal to 1. What is the total stereoisomer? Yes, very good. It is equal to 4 plus 1, it is equal to 5. This is the easiest trick in which we can score maximum questions from each chapter, from the isomerism part of coordination. Yes, hope all of you understood. Complete theory I have be explained. Remaining questions or remaining the DPP solving and all, you have to do it by yourself. I have many PYQs I have added to it, and all these PYQ you can easily find out. All these PYQs you can easily answer it, and just I want to solve one PYQ, and by I want to solve it, I want to add one concept here. Just go through this question. Correct order of the wavelength of light absorbed by the following complexes. I forgot to mention how the wavelength of light absorbed by the complex and crystal field splitting. How it is related is, crystal field splitting energy is inversely proportional to the wavelength of light absorbed. Just note down this point. Higher the splitting energy, lower will be the wavelength absorbed. We all know that energy and wavelength is inversely proportional. That concept only we are using here. Now just check it. CO NH3 3 plus 1 by lambda. All the questions I have added in the slide, and solution also I have added. You can go through it. Because of time limitation, we won't be able to solve it completely. Okay, just I will be solving this question. Correct order of wavelength of light absorbed by the following species. CO NH3 6. It is CO 3 plus. It is CO C3 plus. And second one, CO 3 plus. That is also CO 3 plus. Next one, Cu 2 plus. This one is Ti 3 plus. Now first case it is strong field ligand. Second case it is weak field ligand. That is NH3 and both are strong field. Yes, both are strong field. Now, and in the case of C and D, both are weak field. Both are weak field ligand. Okay, now how we can compare the splitting energy order? Among this, which is having strongest delta O value? Strongest splitting energy value. Very important question. Strongest splitting energy value. I said to you, if the oxidation state, center metal atom, everything is same, then what you have to go through is check the strength of the ligand. Here it is NH3 and here it is Cn. Which is more stronger ligand? Which is more stronger one? NH3 or Cn? Cn is more stronger. Carbon donor are stronger ligand. So the strongest one among all these is B. Splitting energy order. Delta O order. That is B. Then comes A. Then comes A. B. Then comes A. Then what about C and D? C and D both are weak. Both are same ligand. H2O, H2O. Among these, which is more stronger? Cu2 plus or Ta3 plus? That also I have mentioned. Ta3 plus. Very good. Because higher the oxidation state, higher will be the splitting energy and higher will be the stability. So then comes D. Then comes C. This is the delta O order. And if this is the order of delta O, then what is the order of lambda? Lambda O. Lambda order. C will be greater than D, then A, then B. So this is going to be the answer. What is the answer? Yes, option A is the correct one. So this is the point we have to add in this. So maximum things we have covered. Next is your time to solve the questions. and make a complete clarity about this chapter, because this is one of the high weightage chapter, and high weightage chapter in the inorganic. Most of the questions you can expect from most of the questions from the inorganic you can expect from chemical bonding and coordination complex. So have a good understanding of it. Yes, so that's all about today's class, students. We'll be seeing you tomorrow. Tomorrow is a mock test day, so all of you prepare very well for the tomorrow. Then we will be doing mock test preparation on Monday. Then we will be doing 2 more chapters, that is chemical kinetics and solutions chapter. So yeah, so hope all of you understood all the things clearly. We will be winding up this section. Thank you all for joining. Yeah, go and have the lunch and come back at 3 o'clock for the biology class. Yes, thank you everyone.